Hi, I'm Mike Glass with Orion Technical Solutions. Today I'm going to talk about a feature that's available in nearly all process controllers that's grossly underutilized. All too often, a PID block is simply pasted into the logic, and then some unlucky field tech or engineer is tasked with tuning it. Yet many times, the only way to achieve good tuning and process control is by making use of some of the logic and special PID functionality that is often overlooked. One of many powerful functions that can be helping in many of these situations is using feedforward to bias the controller output. This feature has been available in nearly any controller produced since the 50s or earlier. I'm going to give a simplified real-world example of how this feature can help solve some process control challenges that will hopefully help you understand how you could apply it in your situations. And hopefully this will help stimulate some ideas and spur interest into some of the other PID functions and features that could and should be helping solve some of the other control issues that you're likely running into. The example that I'm going to talk about in this scenario is from an aggregate gravel feeder system that controlled the flow of the gravel uh, based on a weigh scale that was on a conveyor. Because of the physical space limitations of the system, the weigh scale was located some distance from the feeders, and that resulted in about a 5-second transport delay time. And that any of that work with process control know that a pure dead time like that is a real challenge. So what ends up happening is because of that delay, you would have to tune this system incredibly slowly, very, very slowly. And that has a real negative impact on the overall process control if you do that, because if you make a set point change, the system is going to respond very slowly. And that's, in this case, resulted in out of spec product, and i.e. waste, loss of profitability, etc., lower quality, etc. In general, the loop cycle time mathematically has to be about at least 4 times as long as any pure dead time. In reality, it has to be longer than that. So we're talking 20 seconds is the theoretical best. And it's really in this process, it was more like 60 seconds was how they had it tuned and set up with just their simple PID block. It took about 60 seconds to respond. So all of that product was wasted, along with the product on the edges that was suspect, and then they had to dump and be sure, so they had to estimate that. It was a lot of waste, and they were losing a lot of that money because at the end of this process, it's added in some very expensive oil and other stuff, all of which costs money, and all of which was wasted when they would make set point changes or during startups or shutdowns. Um, so what can we do to solve this, or how did we solve this? We're going to talk about that next. So in short, we use feed forward to bias the output to the approximate percentage based on the set point entry. So what we do is we do some test runs, and we create a curve of flow percentage. In this case, it was tons per hour versus the output percentage, which was actually a VFD. So as we ran that, we basically ran from 0 to 100. We were able to do in this case, and we plotted the tonnage, the average tonnage, and created a curve, which in this case was somewhat linear, and you can see that in the little graph below. So from that scaling, we've got this function curve, which I kind of show as the yellow with the function curve shown there. What we do is we basically, the set point feeds into a block in the controller, and that controller scales to produce a rough bias signal. It's basically just a percentage that biases the controller. So that bias basically just adjusts the output by whatever amount you say based on how you set up the PID block and so forth. So what this does is it makes it so that when we run this, if the operator makes a set point change from 70% to maybe 50% on this particular part of the product, the the feed forward is immediately sent in and the output immediately adjusts. It's not exact. There could be slight differences. The gravel might be, more, it might be flow easier one day than another day, and it might have to make a small adjustment, but it's going to be within a couple percent based on that testing. Then the PID block will make up for any small deviations or errors so that steady state, you're spot on. Okay, so to cover this full system, the whole concept, basically what we have is there's a transport delay because of the where the weigh scale is in relation to the feeder, and that's causing a 5-second pure dead time, which makes it where we can't tune the system very aggressively and results in a lot of wasted product during the ramp up or ramp down times. So what we do is we set up that scaling function so that the set point comes in and feeds the scaling function, which produces an output bias that's fed directly into what we call the bias input of the controller. That just biases the output up or down, whatever you tell it to do. That output then is adjusted immediately, tells the VFD to speed up, slow down, whatever it needs to do. But the PID controller, typically we're running this as a PI controller, and we're typically running it what we call integral dominant. It's mostly doing integral function. We back off the gain and we let integral do most of the work because we want that part of it to just be very slow and smooth. So basically the end result is that you have a very quick reaction. You get really close really quickly when you make a set point change, almost instantly. And you also are able to keep a very smooth, not oscillating, cycling, fluctuating process that basically is steady state, spot on. So you get really good quality, minimal off-spec product and waste and so forth. So it's kind of the best of both worlds. And I always tell people process control is always a compromise. In this case, we kind of cheat the compromise. And you can often do that if you use these kinds of functions and blocks and you be a little more strategic. So the feed forward bias feature that I just discussed, it's just one of many possible options, features, and so forth that are available on controllers to help solve various issues that come up. Always be ready to think outside the box on this. In this case, think outside the PID box, if you will. Analog controls, like I say, there's always going to be these compromises between speed, stability, minimizing errors, etc. But if you're smart about it and you really look and you understand the controller that you're working with, the logic, and understand the system, watch the operators, talk to the operators, understand how to operate the system optimally, you can often find solutions that are a little bit there's a little more than just a simple PID block, but it's going to run way better. Um, so it's important for any process control practitioner, control engineer, automation specialist, anybody like that, to really understand not only the theory of process control at a pretty solid level, but also understanding the functionality and the feature of controllers, and even tuning methodologies and so forth. So a lot of that stuff seems to be missed by most of the generic textbooks, even textbooks with the name process control. However, there is the one that I use the most that I found, I don't know, a long time ago, and it is fantastic. It's one of my most used references. It's Process Control for Practitioners. It's by Jacques Smuts with opticontrols.com. And you can find it on the web. I think it's on Amazon for like 103, but you can buy it directly from them too. And he has other stuff. He's a true guru. He's the real deal. And that book is laid out better than anything I've ever seen. it really solves the problems and gives you a lot of insight into process control. And like I said, it's mine. I've used it a lot. Little stickies all over the place. So kudos to Jacques. We need more of that kind of stuff published. So yeah. Okay. So in closing, our process control training and our process control courses provide really good coverage of these kinds of concepts, and they're really designed for folks who are tasked with solving the real problems you can run into in the field. It's not a mathy, pure theory course. It's very pragmatic and practical. There is some theory involved, but we make that very easy to understand and easy to implement, so that we can actually, produce a measurable impact back in the plant. So you can contact me anytime to discuss this. If you have questions, input, my contact info is down at the bottom on the left there, and we appreciate your interest. Thanks.